Now we can ask ourselves, what is the value of a? In order to do that, we need to normalize the function. The function is sine of x is equal to a. Thus, we need to find the value of a. A, sine of n pi x over L. Well, for that, what we need to do is we need to integrate. Okay, we know that we have sine of x, and we're going to do the time dependent. E to the negative I e t over h bar times, this is going to be psi star. I'm going to put something now so that you can understand. Times psi of x e to the negative I t over h bar. What this is saying, what I'm saying is that this here, the integral of psi of x star psi of x dx must be equal to 1. So all of this right here must be equal to 1. What are the probability of finding the particle inside the box? 1, 100%, just 1. We cannot find it outside, we can find it inside. 100%, one time. So then, this here, remember when you use psi star, you need to multiply by the complex conjugate, okay? And what is going to happen is that psi x, when you multiply by the conjugate, this is going to become positive. And positive and negative over here, this cancels. This cancels right here. They cancel. So now you stay with psi of x, psi star x times psi x must be equal to 1. And you want to also get this and divide it by psi x times psi of x, right? But look, we don't need anything of this in the bottom right here, in the because we don't have no complex number over here. We don't have no i's or anything, so we can get rid of all of this right here. We can even get rid of the star right here. And we could write this as this right here. Psi of x and psi of x is equal to 1. Probably so what are we doing? We're squaring. And remember, the function is a. So we have 2a, so I need to take an a square out, okay? And I'm going to get what? The integral. That'll be sine square of what? Of n pi x over L. Over L. To work this integral right here, we have an identity, a trig identity that says the sine square theta is equal to 1 minus 2, 1 minus cosine, sorry, 1 minus cosine 2 theta. Well, if we use this, we can say that the integral, right? We're going to say now we're going to use it from 0 to L. From 0 to L Okay, if I integrate this, okay, I'm going to get my a squared. My a squared is equal to my integral from 0 to L, and this is, I'm sorry, this is over 1 minus cosine 2 theta over 2. From 0 to L of 1 minus cosine 2 n pi x over L. And we know one thing about this, because we don't want to work it all out. We know we're going to get two terms. One is going to be a 0 term, and the other one is going to be 1/2. So we know that this is going to be a squared is equal to the integral, okay, from 0 to L of dx over 2. So my a squared is going to be x over 2 evaluated as 0 and L. And what I'm going to get is, I'm going to get that this is equal to, and all of this is equal to 1, remember. All of this right here is equal to 1, okay? So I'm going to get at L, I'm going to get L over 2, and at 0, I'm just going to get a 0. So all of this is equal to a squared L over 2 is equal to 1. So my a is equal to, right, taking the square root and everything, moving everything to the other side, it's going to be the square root of 2 by L. So now my function, my eigenfunction, side of x, is going to be equal to the square root of 2 over L sine m pi x over L. That is my eigenfunction. Okay? So now, and my eigenvalue is going to be E equals n squared pi squared h bar squared over 2 m L squared. So I have my eigenfunction, found my the value for my a, and I have my eigenvalues. So now, looking at this right here, I know, okay, let me erase this for a second. I know that my first energy stage is going to be like this. And I know that at this level right here, let me explain something. My function does something like this. But remember, what are we going to do? We're going to square, okay, the function. And when we do that, we're going to square it. And when we do that, we're going to see that when we take the square, we're going to see that square of side of x, this is going to go and do, it's going to be like this. It's going to have maximum, it's going to be like this. I'm trying to do my best. And it's going to come small like this. Okay? And this is right here. And this will be my lowest energy value, will be my n squared pi square h bar square over 2m E. My second energy, it'll be twice. It'll be 4 pi square h bar square over 2m E. It will have one node. Like this. My other will be 3, so that'll be 9 pi square. Remember, it's integers, so 1, 2, 3, n is the value of that. H bar square over 2m, it's L square. This is L square. L square right here. This is the energy. L square, and L square. Then the other one will be how much? Here I will have how many? How many nodes? I will have 2 nodes. See if I could do this. From here, from here. Let me see if I could do it like this. One right here, and one right here. And this will go like this. It will go like this. I'm trying to do my best. And it will go like this. Then the other one will be 4 times. That'll be 16 pi square h bar square over 2ml square. So now this one right here will have 3 nodes. Let me see. We'll have something. Let me see. 1, 2. Start like this. Go up like this. Come down like this. And then just go up like this. We'll have 1, 2, and 3 nodes. So the next one will be 5. So now we got our normalization process. We found the value of A. Have our energy values, and the this right here, because I need to explain that somewhere else. This right here will be of this form like this, and you can see that the energy from here to here, right? This one is bigger. It's bigger. This one is also bigger than this one right here, because it's 9 times, and this one also is bigger because it's 16 times. It's 16 times. So I hope you like this video. If you like it, please hit like and subscribe. Thank you.